Welcome to another podcast. In this episode, we're going to be taking a look at a different way of representing the Laplace transform of a power function. And it actually involves one of the most important functions in all of mathematics, something called the gamma function. So let me remind you of what we had last time. We found that the Laplace transform of t to the n was n factorial over s to the n plus 1. And I actually want to maybe go a different route with this because this only works if n is a integer, and in particular n is a positive integer. So n is values like 0, 1, 2, and so on, these discrete whole number values. We would like to know what is the Laplace transform of something like t to the 1/2, but the immediate difficulty is what is 1/2 factorial? Does this even make sense? Can we even do that? So I would like to expand on allowing any value of n to be a part of this. I just don't have a good way of doing it with the formula that we produced last time. So instead, let's give it another shot from a different perspective. The Laplace transform formula says that this will be given by this particular integral. And I actually want to do a change of variable here. So I want to let t be equal to u over s, in which case dt is du over s. And so we would have the integral from, well, if t is 0, then u is 0. And if t is infinity, then u is infinity. So the limits of integration won't change. I replace t with u over s. And e to the minus st becomes, well, if t is equal to u to the s, then st is equal to u. So this becomes e to the minus u. And dt gets replaced with du over s. So what we end up having in this case is n copies of s here, one copy of s here. So it's 1 over s to the n plus 1. I can pull that outside the integral because the integral depends on u. The integral from 0 to infinity of u to the n, e to the minus u du. And what's nice about this is out pops a very nice function called the gamma function. And so the Laplace transform of t to the n is equal to 1 over s to the n plus 1 times something called the gamma function, and it turns out to be the gamma function of n plus 1 in this case. So what is the gamma function of n plus 1? Well, it is this thing I have underlined in blue. The gamma function of n plus 1 is defined as the result of integrating u to the n e to the minus u du. Now, that is an incredibly difficult integral to evaluate by hand. It's one of those challenging ones that we might give you in Calculus 2. For good reason, though, it's challenging. That involves several integration by parts right after one another. It turns out that when n is 1/2, it's extremely difficult to do. But we do have some nice formulas here. So a couple of maybe properties, if you will, of the gamma function. The first property is that the gamma function of 1/2, so this when n would be negative 1/2, so it's the integral from 0 to infinity of u to the negative 1/2 e to the negative u du. Turns out that quite miraculously that has a value of square root of pi. Now that's not something I'm going to spend time to show you how to do. You could probably find it in an advanced calculus text. But the gamma function at 1/2 is the square root of pi. But by far the most important property for us here is that the gamma function of n plus 1 is equal to n times the gamma function of n. In other words, when you do one integration by part, you get the n to come out, and then you're looking at u of n minus 1 for the next integral. Because of this, they have this nice property that, well, if gamma of n plus 1 is n gamma of n, then that means n minus 1 gamma of n minus 1. And you can keep kind of going through this motion to prove that this ends up being n factorial. So there were two major formulas here. Make sure that you don't want to miss them. One of them is this relationship, gamma of n plus 1 is n gamma of n. And the other important relationship here is gamma of n plus 1 is defined to be n factorial. So both those are important to hold on to. But here's the wonderful thing about this. This formula, because it's based off an integral, because it's based off the value n in the integral, I don't have the same restrictions on it that I would have on just placing n factorial into n factorial the way we know it. In fact, it turns out that this formula is valid for n greater than -1. All values. Meaning, if you ever wanted to know what is -1/2 factorial, if such a thing exists, it does. -1/2 factorial would be gamma of 1/2, and we just said previously that gamma of 1/2 is the square root of pi. So that's kind of astonishing. Let's maybe look at an example here. What is the Laplace transform of 4t to the 3/2? Well, that would be 4 times the Laplace transform of t to the 3/2. And according to our formula, that's going to be gamma of 5/2 over s to the 5/2. Notice that in our formula that we have right here, the n plus 1 in the gamma matches the n plus 1 in the s. And actually, that's an okay answer. We can actually come up with a better answer because of the way the gamma function works. This is 4 times gamma of 5/2 using this property is the same thing as 3/2 gamma of 3/2 over s to the 5th, 5/2, which is the same thing as 3/2 times gamma of 3/2 using that property is 1/2 gamma of 1/2 over s to the 5/2. And we know that gamma of 1/2 is the square root of pi. So if you look at everything you have here, you've got 4 times 3/2 times 1/2 times the square root of pi over s to the 5/2. And if I clean that up a little bit, that's the same thing as, let's see here, we get 12 over 4, so that's going to be 3. Square root of pi to the 5/2, and typically people will write it like this. Square root of pi over s to the 5th, because that would be s to the 5/2 here, and square root of pi in the top. But basically the idea here is, because we know the value, because we know that gamma of 1/2 is the square root of pi, so this is another good formula to remember here. Because we know that that's the case, then what that allows us to do is, if we start with any power involving 1/2, then we can use the gamma function's properties to get it down to gamma of 1/2, and so our answer will involve the square root of pi somehow. This also gets us back to the question that I wanted to ask at the very beginning, and that is, what is the Laplace transform of t to the 1/2? Well, the answer to that is, it is gamma of 3/2 over s to the 3/2. But as we've seen here, gamma of 3/2 is 1/2 square root of pi s to the 3/2. So that's the formula for the Laplace transform of the square root of t. So this is I hope you found this to be a very interesting video. The gamma function is one of the more important functions in all of mathematics, if for no other reason than it allows us the ability to plug in negative values into the factorial, fractional values into the factorial, up to -1. Now I cannot ask you what is -1 factorial. In fact, that doesn't exist, right? If you think about multiplying the negatives there, it just doesn't end up working out. But anything short of -1, so if we're higher than -1, I can plug that into the factorial and use the gamma function to calculate it. Now, the gamma function isn't going to be a substitute for knowing that 3 factorial is 6. That would be sort of ridiculous to use the gamma function for that, but if it's not one of those integer values, then the gamma function can allow you to calculate the factorial for each of those cases. All right, thank you for watching.